Good afternoon, everyone, unless you're in Perth like me, where it's still the morning. And of course, before I begin, I'd just like to thank Iman for inviting me here, and in particular for organizing this seminar series, which I think is a really great idea to keep our systems and control community connected, especially in this travel restricted era. I'm Ben Yi, as Iman said, and I'm currently at the Optus Curtin Center of Excellence in Artificial Intelligence. If you're wondering whether you've dialed into the wrong Zoom meeting because the title of the talk is not the same as what's been advertised, not to worry. The technical content is all the same, but I felt like perhaps giving a different story would help to flesh out some of the ideas more. So, before I begin, I want to thank my collaborators on this particular work, Professor Ming Tao from Groningen, where I did my postdoc, Professor Ji Liu at Stony Brook, who's been a long-time collaborator, and my PhD advisor, Brian Anderson. If you find the talk today interesting, then you can check out the extended treatment on archive, and there'll also be a conference version appearing in the IFAC World Congress. Today, I'm going to divide the talk up into three parts. First, I'm going to introduce the area of work, which is mathematical modeling of epidemics. And I think everyone is much more aware of this type of issue because of COVID-19. I'm going to talk about metapopulation models and one of the most classical models known as the susceptible, infected, and susceptible model. Then in part one, I'm going to talk about some work we've done to analyze distributed feedback control of the SIS network model. And part two, I'm going to show you the type of analysis toolkit we had to develop in order to analyze such a nonlinear model. Of course, I think everyone's aware of what an epidemic is now. To give it a more precise definition, we call an epidemic the rapid spreading of an infectious disease in a large population. So typically we're interested in human populations, but you can well imagine other biological species might be of interest. And what's quite important is that in epidemics, there are spatial and temporal elements to the spreading process. Any mathematical model that you develop really should capture both of them. So to give us an example, here's some data I pulled actually back in May. So already this is probably quite outdated, but nonetheless, on the left-hand side, you can see the temporal elements of the epidemic spreading process for COVID-19. These are some of the most impacted countries at the time. And you can see some similarities in the way COVID-19 spread and also some differences. On the right-hand side, we see the spatial elements of the spreading process. So the outbreak began in Wuhan here, but in terms of the spatial patterns over which it spread in the next couple of months, you can see it's very complex relative to the geographical distance to Wuhan. So there's a temporal element to this as well. And of course, related spreading processes might be the spreading of rumors in online social networks, the spreading of computer viruses or opinions or innovations. But today we focus specifically on diseases in human populations. Now, the next thing I want to introduce is the concept of a metapopulation network, which Richard Levins, a famous ecologist, he described it as a population of populations. How can we understand that? The easiest way is, of course, just to look at our world, or at least imagine the world a year ago. Globalization in the last century has created a very interconnected world where we have populations which might be cities or countries that are spatially separated, but we can easily travel, or we could easily travel between them in a travel network. So this here would form a metapopulation network. And we all know now that diseases can spread from one large population to another because infected people from one population come into contact with people in another population. And so the key questions we want to focus on is, can we mathematically model the spreading of a disease? And that's where mathematical epidemiology focuses on. In our case, especially from population to population. And supposing that we have some appropriate dynamical models, then as systems and control engineers, how can we apply the sort of vast tools that we've developed over the last century to help address an epidemic outbreak? So to summarize today's talk, the motivation is the observation that diseases spreading in human populations are a serious threat. I think everyone appreciates that now. And more importantly, control is often required to stop an epidemic or a pandemic, especially for emerging diseases where we have no immunity built up. What I'm going to talk about today is the susceptible, infected, susceptible model. It's a classical model for disease spread over metapopulations. And I'm going to look at a broad class of distributed feedback controllers and look at how they perform. And then I'm going to talk about some tools from differential topology and monotone systems theory that we used in order to analyze these feedback controllers. So let's turn to the very fundamentals of the SIS model. I'm going to, in the first case, consider a single well-mixed large population of individuals, and the population size is constant. So the birth and the death rate is equal. Here's a very toy example with only a couple of individuals. When I say well-mixed, it simply means every individual has a probability of coming into contact with every other individual. So obviously this isn't going to describe interactions between two different cities, but at least on a smaller resolution, it's perhaps appropriate. And each person has two possible health states. The first is susceptible. So here we have a blue individual. And we have also infected individuals who have been infected by the disease of interest, and they're denoted by this red node. And so these individuals come into contact with each other. One of the assumptions we're going to make is that individuals recover with no immunity to the disease. So for example, influenza is appropriate for the SIS model. But if we're considering COVID-19, for example, although there is still ongoing research as to whether or not you can contract COVID-19 twice, the current experts consider that once you've recovered from the disease, then you're immune, which means the SIS model is not appropriate for COVID-19 modeling. Now, if you're susceptible, then you can become infected by coming into contact with an infected individual at a rate B, which is called the infection rate. And if you are infected, you can recover with a rate D, called the recovery rate. And so you can imagine the recovery rate might be influenced by immunity, the natural response for humans, and medical interventions. What we're going to do today is study the deterministic model. So we'll, in the next couple of slides, look at some continuous time ODEs. It is a mean field approximation of a stochastic model. And so we can ask questions about how accurate that mean field approximation is. Some works do look into this. I'm not going to explore that direction today. What I do want to comment is, at least from my understanding, the medical community do consider deterministic models to be appropriate. So Jodie McVernon, who released one of the preprints back in March on modeling that informed the Australian government of their response, those were based on deterministic models. So at least we know we're roughly in the right area. Now I'm going to denote with capital N the constant population size, and capital S and I respectively as the total number of susceptible and infected individuals in the population. That means this equality is going to hold for all time. Using X to represent the proportion of the population that's infected, this means if X is equal to 0, no one in the population is infected, X equals 1, everyone's infected with the disease. The single population SIS model can be written like this. So the proportion of infected decrease based on the recovery rate D, and increase based on the infection rate times the susceptible proportion of the population interacting with the infected proportion of the population. Now, it's relatively easy to show that if the recovery rate is less than or is greater than or equal to the infection rate, then as t goes to infinity, x is going to tend to 0, which means in the physical context, the disease is eradicated from the population as time goes to infinity. On the other hand, if this inequality does not hold, and you initialize the system at any point other than the origin, then as t goes to infinity, x tends towards a positive value between 0 and 1. And that means the disease is endemic, or it's always present in a proportion of the population. So it's a relatively simple threshold type behavior where, depending on the parameters, you get two different types of outcomes. Moving on, we now look at a metapopulation network. So in the previous slide, I was talking about a single population. We now have a network of n nodes labeled 1 through to n, where node I represents a population of size capital Ni. So here in this example, the blue node is population I. And these are the neighboring nodes or the neighboring populations of population I. You can think of a neighbor as any node that has a link, and this link represents some sort of infection transmission between the two populations. So now I'm going to write each node, the dynamic equation of each node as follows with a subscript I. The first two terms are the same as the single population model, and what I'm adding here is some dummy term that represents the infection from neighboring populations. Now, if you go through some derivations, I'm not going to show them here, but what you'll eventually get is the following, which is what is known as the SIS network model. And so just to reiterate, XI is the proportion of the population that's been infected for population I. Bij is non-negative, and in fact, if it's positive, it means that the individuals from population J can infect the susceptible individuals in population I with a rate Bij. So in this example, if this is population J and Bij is greater than 1, it means individuals from population J can infect individuals from population I. And BII is simply the intra-population infection rate. NI is a mathematical definition of the set of neighbor nodes of I, but that's not especially important. This model has really been studied across many different communities for almost 5 decades. So it's no surprise that a lot of its properties, including convergence and equilibria, are well known. So you can see that one of the very first and most classical papers was in 1976, but very recently our community has also started looking into the SIS model. So over the next slide, I'm actually going to show you what existing work has identified, and then I will talk about the new work that we've contributed. So the first thing I'm going to do is write the dynamics of the entire network. And to do that, I collect all of the vectors X, all of the node states Xi into a single vector X. And D is the diagonal matrix of the recovery rates. B is a non-negative matrix of the infection rates between the populations. We assume that the network is strongly connected, and that's equivalent to the matrix being non-negative and irreducible. If we initialize the system so that every population has an initial condition between 0 and 1, then it's quite easy to check and to prove that for all time, the trajectory of the system is going to remain inside this unit hypercube. Now that's quite important because it means our model is well defined and we're always preserving the physical meaning of the state variables. The next thing I want to do is define a reproduction number R0 as the spectral radius of the matrix D inverse B. I think we've all sort of come across this number in media or news, and we're going to see exactly how that shapes out in the SIS model. In particular, if the reproduction number is less than or equal to 1, then the origin, or the vector of all 0 entries, is the unique equilibrium for this SIS system. And in fact, this is a necessary and sufficient condition. And this origin equilibrium, or what we call the healthy equilibrium, is globally asymptotically stable and exponentially so if the reproduction number is strictly less than 1. That means over time, if the reproduction number is less than 1, we're going to converge to the equilibrium where every single node is free from the disease. Conversely, if the reproduction number is greater than 1, then the healthy equilibrium, or the origin, is unstable, which is perhaps not good news. And there exists a unique endemic equilibrium, which we denote by X star, with entries strictly between 0 and 1, and it is exponentially stable for all initial conditions other than starting at the origin. So it means when our reproduction number is greater than 1, as t goes to infinity, every population is going to have some proportion of its individuals infected with the disease. Now, knowing that the reproduction number really quantifies all of the possible outcomes of the SIS network model, of course, we want to try and improve a situation where the reproduction number is greater than 1. So in terms of existing control methodologies, almost all the works adopt a type of single shot approach where you set parameters such as the recovery rate or the infection rate, or you remove nodes and links in the network in order to minimize the reproduction number, preferably to actually reduce it to being less than 1. But that means these approaches do not allow for adjustments as the network or the epidemic characteristics change over time. And we know from COVID-19 that the network can change over time as travel restrictions are imposed, and the epidemic characteristics are also changing over time as we learn more about the infection rates and the recovery rates of COVID-19. You can imagine that a budget might be imposed on the allowable adjustments in order to reflect the real world where we have a limited number of resources. And so often there's an optimization problem that's formed to determine how best to change parameters, nodes, or links. And in many of these cases, we need a centralized approach that requires knowledge of the network structure and the parameter matrices D and B, which are the recovery and infection rates. So these are the existing works, and now I'm going to consider a different approach, which is distributed feedback control. We're looking at the SIS network model. What I'm motivated to do is to develop a distributed controller, especially for the case where the reproduction number is greater than 1, because we know from existing results that when the reproduction number is greater than 1, we converge to an endemic equilibrium. So my idea is to use the recovery rate, DI, as the input for the feedback control. And why might we do that? Well, feedback control is one of the foundational tools of control theory, so it makes sense to try that. You can imagine DI as representing health resources, or the amount of medical attention placed on a single population. And so you might want to change that dynamically as needed. If the infection grows, you might want to pour more resources into a particular population. And coming from a distributed control background, of course, I think distributed control would be nice if we can pull it off. because it means that our control for any population depends only on xi. So you don't have to worry about what the other populations are doing as long as you keep an eye on the infection level of your current population. Then you can implement the controller. So these are the potential advantages, and we're going to see how they actually play out when we try to implement the feedback control. In particular, I look at a class of controllers of the following form. DI is the base recovery rate of population I, so it's constant and positive. And then HI is the control input. It's a smooth, monotonically non-decreasing function, and it satisfies that HI is 0 when XI is 0. Then I modified the SIS dynamics from above to this form below. So I've replaced the base recovery rate of population I with the summation of the base recovery rate and the control input represented by HI. If we consider HI, it's a very, well, it should cover a broad class of functions and therefore controllers. These are relatively relaxed assumptions, and they're also quite reasonable because it's telling us that whenever the infection increases in a population, then you either keep the control input constant or you increase it. And that's quite intuitive when we consider that XI represents the proportion of infected individuals in the population. So the first thing to do is look at when we might be able to stabilize to the healthy equilibrium. Now I'm going to again write the network dynamics as follows. So it's very similar to the original SIS model. D is the diagonal matrix of recovery rates, H is the diagonal matrix of control inputs, and B is the non-negative infection matrix. What we show is that if the uncontrolled system or the uncontrolled network has a reproduction number less than or equal to 1, then for the controlled system, the healthy equilibrium is the only equilibrium of the system. And for all initial conditions, you converge to the healthy equilibrium exponentially fast. So in a way, this is a sort of sanity check, and it's telling us it's good because if the original system converges to the healthy equilibrium, adding control isn't going to mess things up. And this is a sanity check, but it's not the main result we want. What we really want is to consider what happens when the infection rate is, or the reproduction number is greater than 1. So unfortunately, there's some bad news in this case, because what we prove is that if the reproduction number is greater than 1, then the controlled system has a unique endemic equilibrium whose entries are strictly between 0 and 1. We denote it by X bar star. And unless you begin at the origin, then for all other initial conditions, the system is going to converge to this unique endemic equilibrium. And what that means is, for this very broad class of distributed feedback controllers I've introduced, we cannot actually eradicate the disease if the uncontrolled network itself does not converge to the healthy equilibrium. So I guess that's not so nice to find out, but there can be some important contributions from feedback control. First, I'm going to again consider the case where the reproduction number is greater than 1. And I'm going to also make a very mild assumption that there's some population where the control input is not identically 0. So that means we can consider a network where every population has 0 control except for a single population. We know from our previous slides that both the controlled and uncontrolled system each have a unique endemic equilibrium. And what we prove is that the equilibria satisfy the following inequality for all I. What this means is feedback will improve the steady state infection level for every population, even if we can't eradicate the disease completely. So for every population, the final proportion of infected individuals is less once we add feedback control. So although we can't eradicate the disease, we've at least moved a couple of steps forward. The best way, of course, to illustrate that is by an example. Here I have selected some toy infection rates and base recovery rates to give a toy example. These aren't representative of any real disease or from real data. It's a two-dimensional model, so we have two nodes or two populations, and the reproduction number is about 1.63. What we see here is that in the uncontrolled network, the vector field plot shows all of the trajectories converging to the unique endemic equilibrium X star. When I add some feedback control, again, I've selected these as toy examples as opposed to any particularly meaningful control functions. What we see is that still all of the trajectories in the controlled network will converge to a unique endemic equilibrium, but this equilibrium is much closer to the origin compared to the uncontrolled network. So this is, I guess, an illustration of the theoretical result that we establish. Now, to wrap up part one, I've considered a broad class of distributed feedback controllers for the classical SIS network model. And these controllers cannot eradicate the disease when the uncontrolled network does not converge to the healthy equilibrium, but at least feedback improves the steady state infection for each population. Of course, that means a great deal of work remains. And in particular, can we look at more advanced or more complicated feedback controllers to actually eradicate the disease? That will be something for the future, but what I want to talk about in the next or the remaining part of the talk is the approach that we developed to study nonlinear or general nonlinear systems and how we applied that to the SIS model with feedback. So to motivate this part, we're going to use the SIS network model as the example. And again, here is the network dynamic equations. When we look at the situation of the reproduction number being greater than 1, then most of the existing results take some very similar approaches to proving uniqueness of the endemic equilibrium. And in particular, they do some very complicated algebraic manipulations based on the equation here in order to prove by contradiction that there cannot be two endemic equilibria. So once you've proved that it's unique, then you can look at convergence by construction of a Lyapunov function, something that everyone in systems and control is comfortable with. But construction of this Lyapunov function really depends on the functional form of the endemic equilibrium, and in particular, it depends on the fact that it is unique. Which means if you change the dynamics of the SIS network model, each time you change it, you need to repeat steps 1 and 2, and there's no guarantee that you will be successful. So what are some changes? Well, one of the changes that we've already explored is feedback control. When we add an additional term here to represent a control effort, then we've changed the equation, so we would need to repeat steps 1 and 2. Adding further nonlinearities like invasion threshold functions, which represent more realistic diseases, or modeling a different way for people to move between populations. And in fact, this third point was really what kickstarted our adventure into this area, because we looked at a slightly different SIS model, which was more appropriate for capturing long-range travel between populations. And we found that steps 1 and 2 couldn't work at all. So that was where we got stuck, and we started looking at these different types of analysis techniques. More generally, if we consider some general nonlinear system, for systems that model biological or social dynamics, then typically we are interested in equilibria other than the origin, because the origin is where the biological process or the social dynamics has completely ceased to exist. And analysis of non-zero equilibria can be challenging because we want to understand how many equilibria there might be for this nonlinear system. We might want to understand what the stability properties are for the different non-zero equilibria. And if we find from simulations that there's a constant evidence of convergence to a unique non-zero equilibrium, then we'd be interested to identify what sorts of conditions exist to guarantee that the system has a unique non-zero equilibrium. And of course, analyzing the equilibrium typically or often comes before convergence analysis. So all of these points motivate us to develop some general tools to identify or analyze equilibria for nonlinear systems, especially coming from biological and social fields. In order to do that, we have to go to a different area of mathematics and back a century or more to the Poincaré-Hopf Theorem, where Poincaré developed the two-dimensional version in 1885, and Hopf provided the n-dimensional generalization in 1926. And the theorem, or at least one version, a simplified version of the theorem, reads something like this. We consider a smooth vector field F with isolated zeros xi on a compact manifold. And if this manifold has a boundary, then we assume F points outwards at all boundary points. Assuming all these things are satisfied, then the following equality holds. So you might be sitting there thinking, what did I just talk about? Well, hopefully over the next few slides, I can give you at least an introduction to what the Poincaré-Hopf theorem is. First, we might think of a vector field F as defining an autonomous system, x dot equals f of x, and a zero of the vector field is an equilibrium of the autonomous system. So those of us who are more used to thinking about dynamical systems, nonlinear or linear systems, can then relate that to a vector field and a zero. And a zero is isolated if there exists a small neighborhood around it with no other zeros. So again, in the context of dynamical systems, we are talking about isolated equilibria as opposed to a line of equilibria. Pointing outwards has a technical definition, which I won't go into here. There's a lot of notation and additional concepts that are involved, but it has an intuitive interpretation which is consistent with what we consider, what we think about in geometry. So in this particular example, these red arrows represent the vector field on the boundary. And so if the vector field points outwards from the boundary, then that's what you can consider. dfx is the Jacobian of f evaluated using a local coordinate basis at the point x in the manifold. So if the manifold has the same dimension as the embedding space of the system, then you can just directly compute the Jacobian. But if it has a lower dimension, you need to use a different coordinate basis. But again, those are some technicalities which are expanded in the archive paper. For today's talk, we can bypass this. Now, this term here, sine of det dfx is +1 or -1, depending on whether the determinant of the Jacobian is positive or negative. So once you can compute the Jacobian at a particular point, if you can identify whether its determinant is positive or negative, you know this quantity here. Chi of D is the Euler characteristic of the manifold D. This is an integer number that's associated with the manifold itself, and it's a topological invariant. What the Poincaré-Hopf theorem tells us, and what I find quite remarkable, is that the left-hand side does not depend on the choice of the vector field, but rather it is strictly tied to properties of the manifold. So that means no matter what vector field you pick and you put it into the manifold, it has to obey this inequality, or this equality. And it's quite powerful too, because it provides a link from local properties, which is analysis of the Jacobian, to global properties, that is the Euler characteristic of this manifold or space that we are considering. The next thing I want to talk about is the concept of a contractible space. And we say that two spaces X and Y are homotopy equivalent if, roughly speaking, X can be continuously deformed into Y and vice versa. So on this particular animation, then the green blob is homotopy equivalent to this small dot, because you can see it can be continuously deformed into one another. And a space Y is contractible if it is homotopy equivalent to a point. So again, this example here at the start, this green blob is homotopy equivalent to a point. And therefore, this green blob is contractible. And such a space has an Euler characteristic of 1. So spaces which are contractible include the m-dimensional disk, unit simplex, hypercubes, convex polytopes. Spaces which are not contractible include an annulus, the torus, and the sphere. Now we're going to look at how we can use the Poincaré-Hopf theorem to analyze a nonlinear system. And the main theorem that we've developed considers a system or an autonomous system where F is smooth. And we assume that it is operating inside an m-dimensional manifold that's compact, contractible, and smooth with a boundary. And at every point on the manifold, the system points inward into the interior of the manifold. If we can, if the Jacobian evaluated at every x bar satisfying f of x bar equals 0, if the Jacobian is Hurwitz stable or having eigenvalues all with strictly negative real part, then there exists a unique equilibrium x star inside this manifold, and x star is locally exponentially stable. So to reiterate, what we need to do is look at the system and analyze its Jacobian at every point that satisfies this equation, f of x bar equals 0. And if the Jacobian at every point that satisfies this equation is stable, then in fact there is a unique equilibrium for the system inside the manifold. And there is an effectively identical counterpart for discrete time systems covered in an ECC paper by Brian and myself in 2018. So how can we apply that to the SIS model with feedback? To recall, this is what the equation looks like for the SIS model with feedback, but we can hide all of this into a single f of x. And the first thing we need to do to apply the Poincaré-Hopf theorem is to identify a manifold D that has these properties of being smooth, compact and contractible, and on the boundary, the system points inward. So if the reproduction number is greater than 1, then what we can show is there's a vector y, a positive vector y, and a sufficiently small scalar epsilon such that the manifold defined by this equation satisfies the requirements on contractibility and inward pointingness. Of course, again, a better way to talk about this is by an example. So here we have a two-dimensional system with x1 and x2. The original state space which the SIS model operates in is this large rectangle in the gray. And D is simply this rectangle, but with the gray area, or this L-shaped area removed. So really it's a subset of the original state space for the SIS model. Here I've shown a very large L shape, but really it's a very infinitesimally small removal because epsilon is small. And then you can use some basic, very straightforward calculations to show that at any point on the boundary, F points into the red zone, which is this manifold D. On the corners, you need to do a little bit of smoothing because the original D has sharp corners, but again, it's a very small technical issue that can be easily overcome. All in all, it means that for the SIS model, we can find such a manifold. And so the next part is to prove that the Jacobian is stable for all points that satisfy this equation here. Now, because of the issues of time, I'm going to skip this, other than to say that most of the analysis relies on what is known as Metzler theory or M-matrix theory, and these are two very well-known linear algebra fields. And so there's a lot of results that we can call on immediately. And the final outcome is we can show that the Jacobian is in fact Hurwitz stable for every equilibrium inside this manifold D. And because of that, there has to be only a unique equilibrium which is locally exponentially stable. Now that we've proved there's a unique endemic equilibrium for the feedback SIS network model, and we know it's locally exponentially stable, what can we actually say about the region of convergence for this equilibrium? Does the system have limit cycles? And if so, are they attractive? There's still a lot to be considered. And as I mentioned before, Lyapunov methods require a Lyapunov function. And it's not actually clear whether there was a single Lyapunov function that you can apply for all of the different types of controllers that are covered by this very general assumption I made earlier. So we want to look for a more general tool for convergence. And of course, the answer is yes, there is one. Again, we look back in time for some inspiration to what is known as monotone systems. In particular, Morris Hirsch in the 80s published a set of very influential papers that identified really powerful convergence results for this class of systems. And for anyone that's interested in this area of work, then I really recommend the review by Hal Smith in SIAM Review. It gives a very nice introduction and overview for this topic. What is special about monotone systems is that they satisfy an order-preserving property. And what we can do is let phi denote the solution x of t for this particular nonlinear system when you initialize it with initial conditions x0. We make some additional assumptions on smoothness for f. And then it's known that monotone systems satisfy a particular inequality where if the initial conditions obey an inequality, then so do the trajectories. This inequality is defined element-wise. And again, here's the illustrative example. We have two initial conditions for the same nonlinear system, which are ordered. And so the trajectory at any point in time also obeys the same ordering. And from this particular property, you can prove some general convergence results. We restrict ourselves to a system which is operating in an open and positively invariant set. And the first thing we can do is show that the system is monotone if the Jacobian has non-negative off-diagonal entries for every point inside this open positive invariant set U. So it doesn't matter what we have on the diagonal terms. What matters is the off-diagonal terms. There is a necessary and sufficient condition, which is very elegant, but it requires a little bit more notation, so I've omitted that for the presentation. And if we suppose that the system is monotone and we further assume that the Jacobian is irreducible for all values of x inside this space U, then it's known that for almost every initial condition in the set U, the trajectory of a monotone system converges to an equilibrium in U, which means there is no chaos that is possible and all limit cycles are non-attractive. So here we have already a very powerful result developed for a general nonlinear system using only some properties that you can identify from the Jacobian. What we've done is refined the convergence result. And again, we assume we have a monotone system where the Jacobian is irreducible. If U is convex and the system has a unique equilibrium in U, then in fact, for all initial conditions in U, the system converges to the unique equilibrium. That means when we have a unique equilibrium and U is convex, there will be no limit cycles that exist. And so we can apply that to the feedback control for the SIS network model. Remembering that we earlier identified a space or a manifold D, and we knew that there was a unique equilibrium inside it. We know it's locally exponentially stable from the Poincaré-Hopf theorem. It's quite straightforward to prove that this system is monotone and its Jacobian is irreducible. And so immediately from the monotone systems results, we have convergence for all initial conditions except the origin to this unique endemic equilibrium. Okay, so to summarize, we have used classical results from the Poincaré-Hopf theorem to identify a sufficient condition for a general nonlinear system to have a unique equilibrium. Monotone systems theory is a very classical framework that gives us powerful convergence results without the need for Lyapunov functions. And these two tools can be applied together to analyze distributed feedback control of the SIS network model, which is what I covered in part 1. And to reiterate, the reason why we wanted to do this is to bypass a lot of the complexities from existing techniques that rely on algebraic manipulations and Lyapunov functions. For future work, I'm quite interested in looking at different epidemic models. The susceptible, exposed, infected, removed model is one of the more popular models these days because it is a foundational model to capture COVID-19. And I mentioned before that I'm interested in modeling how transportation flow between populations spreads the infection. There's a model called the bivirus model where two competing viruses spread on a population. And looking back at the distributed control problem, then it might be interesting to control infection rates. We've all seen that as really what governments and local governing bodies really try to look at when they try to control an epidemic. And periodic control might be something else to consider. So that concludes my talk. Thank you. And yeah, questions.
Thanks, Ben, for your talk. It was very interesting. If there's any question, I'm happy to pass it along, or you can ask it directly from Ben. Brian, do you want to ask? Yep. Oh, no, it was Daniel, sorry. Daniel, go ahead. Yeah,
Hey.
sorry. Yeah.
Hello?
Yeah, go ahead.
Hey, Ben, thanks for the talk. It was really interesting. Your stability result was a little bit counterintuitive. So for the uncontrolled case, basically, you have the origin as your stable equilibrium if D is greater than B, right? Or the ratio of the spectral radius, the ratio of the spectral radius is less than 1.
Mm-hmm.
But in your controlled case, you can increase D arbitrarily, right? You could even make it constant and really high, but somehow for the controlled case, you still can't make it make the origin a stable equilibrium. So why is that the case?
Oh, okay. So what I'm considering is D is sort of something you can't touch. It's the innate population-based recovery rate. So it's not something you can actually adjust or control. What you can do is add additional recovery rate through H.
But
So
isn't that
why,
the same thing as just increasing D? Like, aren't you effectively just increasing D?
well, for H, you increase based on the current infection level. So if you just increase D arbitrarily, of course, you can stabilize the system, but that requires a lot of resources, and you have to be, I think, quite strategic in adding constant D. So rather than that, I was interested to see whether you can dynamically change the recovery rate and still achieve stability.
But wouldn't a constant D, wouldn't a constant H still fit the assumptions of your controller? Like, just assume it's a constant. Where does that break?
Well, if it's constant, then I guess you can, it really falls back into, let me just go back. So there are a lot of existing works which look at changing a fixed recovery rate.
Yeah.
So if you have a constant H, what you're really doing is looking at some existing approaches because you can only set H and D at the start if it's constant. But once the epidemic is evolving, then you want something dynamic as the epidemic evolves over time.
Yeah, but I just like your assumptions on what H was, it would also include a constant, right? Wouldn't a constant also satisfy that?
Yes, but then you can just add it to D, and it has no real difference to the.
Yeah, so if you used such a constant H, wouldn't you get the origin as a stable equilibrium? Since it
right, but then
satisfies
you've
the
added a constant amount of resource at the start of the epidemic.
Yeah,
And
I get that, but like, why doesn't that violate your assumptions on H?
Well, it's really just how you can generalize it. So of course you can do that. So I think you're saying, why do I need to make this assumption here?
No, I'm saying, so if you added a constant H, right, you could achieve a stable origin, basically, right?
Yes.
So your H here, right, allows you to do that the way you've
Well, the question then
defined
becomes,
H.
where do you add H? How do you add H? How much H do you add? And so that goes back to these existing works and how they try to address the problem. So
Yeah, but it just seems you set like a fundamental limit that it can't be, you can't get a stable origin no matter how you change H.
Well, yeah, so the idea was to identify that there is this fundamental limit if H is identified this way. If you allow H to be constant, then you can use existing control approaches to address the problem.
Oh, cool. I was just reading Brian's comment. Yeah, I think that's answered it.
Yeah.
H has to be 0 at the origin. Sorry. Yep. Okay. Didn't see that. Yep. Makes sense.
Okay.
Thanks.
Thanks. Okay. I think we are nearly done. I have a bunch of questions myself, so I'm going to email you later. If
Sure.
anyone is interested in asking questions because we are out of time, please contact Ben directly. And thanks again. Thanks, everyone.
Thank you.